Welcome to another episode of Dominic Does DIY. Today we're going to look at the MosFET, and we're going to come to understand on the first episode what it is in the spec sheets that we need to pay attention to. What are the critical parameters, and what is it that they mean, and how do we use them for our design. As always, go ahead and like, subscribe, share, make a comment down below, and let's get into this. So again, we'll be using LT Spice to simulate some things and take a look at schematics. So here we can see we have two MosFET configurations. We have an NMOS set up as a low side switch, and on the right we have a PMOS set up as a high side switch. This is the common configuration that we see in NMOS and PMOS. NMOSs are usually used as a switch to pull something to ground, and a PMOS is a switch that is used to supply voltage to a load. So then when we're deciding what kind of FET we need, we want to be able to size it appropriately for our design, because the bigger the FET, the more costly it is, or the larger in size it is, and we may want to keep our product small and compact. We only want to really spec out something that we absolutely need. We do not want to oversize something just for the sake of oversizing it. So we will look at the spec sheet for the NMOS, the FDS4410. So here we have the data sheet. Again, just like in most data sheets, the very beginning tells us some basic properties that we need to know. In the features section, it gives us our current rating, our RDS on at different gate voltages, our VDS, gives us some typical applications on what it's used for. So let's dive into the data sheet and the specs themselves. So here we can see the first one we want to take a look at is the VDS. So in the VDS, this is the max voltage rating that this thing can hold off when in the off position. So in this circumstance, we have a 5 volt load, our B5P0. So this is 5 volts, and our drain to source is 30 volts. So we are fine. This MosFET is overrated with voltage, more than what we need. This would not be good if, say, our voltage instead of 5 volts up here, it was a 40 volt, 48 volt, 60 volt source. Then this MosFET would be no good. The next one here is the gate source voltage. That is the voltage from the gate to the source. So here we can see we can have a plus or minus 20 volts applied to that gate without causing damage to the MosFET. This will be important to know later on when we get into the threshold voltage of the gate. The next parameter is our drain current. So we can see here our drain current. We have a continuous drain current of 10 amps and a pulsed current of 50 amps. We got to look at the power dissipation capabilities. And in this one, we can see there are 3 different wattage ratings. We have 2.5 watts, 1.2 watts, and 1 watt. So just like there's a current rating for 10 amps, we have different wattage ratings, and they all have notes next to them, say note 1A, 1B, 1C. So then let's go take a look at these notes and see what they're pertaining to. Why is it that this thing is listing 3 different wattages for the same part? And why is the 10 amp rating based on a note? So if we go down, we can see that the notes down here, note 1, it has everything to do with the thermal capabilities of the part. So note 1A is saying that the footprint is going to have a 1-inch square pad of 2-ounce copper in this format. Note 1B says that you will have a footprint that resembles this. And note C says that you will have a basic footprint of just the package itself, just to hold down the leads. In each of these instances, the copper allows us to dissipate more heat. The heat comes off of the drain pins. That is why over here you can see that they connected the thermal relief pad to the 4 drain contacts and not the source or the gate. But when you have a 1-inch square, you can see that their thermal reactivity is 50 degrees C rise per watt. Meaning for every watt of power this MosFET is trying to dissipate, you will see a 50 degrees C rise at the junction. And as we go to the right, our thermal dissipation pad reduces and as such, our degree C rise per watt increases. So you can see here, we go down to all the drain pads and a little bit under the component itself. This is a pretty standard issue pad. I would say that this is probably going to be more of what you are looking at in the real world. But here we can see we have 105 degrees C rise per watt. And this one right here, this is also another standard footprint. But just for the thermal capabilities, I would say for this part, this would be a better footprint design than this one. But since this is a standard footprint, then you probably already have this one in your library and you might just go with it. And in this instance, we still get 125 degrees C rise per watt. So as we get further on, when we start talking about the RDS on and the power dissipation, you can make a determination on what footprint you want to have. So how is it that we can determine the thermal dissipation or what footprint we need? Well, the thermal dissipation required in the wattage created by the MosFET is a product of two variables: the current that you're trying to pass through this MosFET, the ID, and the resistance of the drain to source of the MosFET, the RDS on. So you can see up here, we have an RDS on variable, and there are a lot of different options, again, that we got to look at and we got to consider. So when we're looking at this, we can see that if our gate voltage is 10 volts, then our RDS on is going to be at a maximum 13.5 milliohms. But if we only supply a 4.5 volt to the gate, you can see the maximum the maximum RDS on that we are going to see is 20 milliohms. So the greater the gate voltage, the lower our RDS on will become. Now these are the numbers that are used specifically in the data sheet as a spec to kind of reference, but this RDS on is not the full story of the system. So if we scroll down some, we'll go into the typical electrical characteristics graphs, and we can see by examining the graphs, we can get some more information on exactly what is the RDS on under different circumstances. So we can see that this is the graph for RDS on versus drain current based on different gate voltages. So this is a normalized graph. So we can see here that it is normalized on the 10 volt line. So basically, if we look at what that means is when you look at the spec on the data sheet that was above for 10 volts at 10 amps, that is our one right here. So if we just scroll up, you can see they had a spec here, VGS, 10 volts, 10 amps, and we had 11 milliohms to 13.5 milliohms. But this is the normalized variables. So when we look at the graph right here, we can see one is that 11 milliohms at 10 amps for 10 volts VGS. Now we can look at this graph and we can now see what kind of effect the gate voltage has on the RDS on at different current ratings. So we can see, just looking at 10 amps, if we wanted to push it, we can see that the RDS on for a 5 volt system, let's say you're trying to turn this MosFET on with a microcontroller, you can see that roughly that's about 1.25. So we can say this is probably somewhere around the realm of about 1.4 times the normalized current, or 1.4 times 11 milliohms, which will come out to about 17, 18 milliohms for a 5 volt VGS at 10 amps. So why is that important? We also need to consider what pad we are going to use. So if we were using a 5 volt microcontroller to turn this MosFET on and we wanted to push 10 amps, the question is how much wattage does that come out to? So we can use Ohm's law. We're just saying our current is 10 amps. So I squared R. So 10 times 10 times our 18 milliohms, so 0.018. And that means that we will be pushing 1.8 watts through this MosFET if we were trying to push 10 amps with a 5 volt VGS. What does that mean? Well, now we can go up to our thing here and we can say, okay, well, if I want to push 1.8 watts, then what kind of temperature rise am I going to see on the junction? Well, if we were using this big guy, we can see that it's a 50 degrees C rise per watt. So we take 1.8 and then multiply that by 50. And that says that we would have a 90 degrees C rise on that part to push 10 amps. So of course, that is probably going to be extreme and no good. So even with the biggest pad here, we can see that trying to push 10 amps through this MosFET with a 5-volt gate is not very practical. So then the other thing we need to look at also in the spec is the gate threshold voltage. This is the actual voltage that allows the MosFET to turn on. So we can see here, there's a minimum of 1, a nominal of 2, and a maximum of 3. Of course, this goes across many different components. So they're saying if you buy this MosFET, if you get 100,000 of them, some will be at 1, some will be at 2, some will be at 3. So you got to design around that threshold voltage. In order to design around that, what does that mean? That means that you should ensure that whatever voltage you're putting on the gate is greater than the maximum threshold voltage allowed by that component. So you would want to make sure that whatever you're supplying the gate voltage with, it is greater than 3 for this particular part. Because if you only supply 2 volts, if you say, oh, I'm going to try to turn this on with 2 volts because that's the nominal voltage, you may end up getting a part that requires 3 volts to actually turn the gate on, and you will have inconsistent operation. Some units will work, some units won't work. Always be sure to have your gate voltage greater than the maximum spec value. So also the RDS on that we were speaking about earlier, not only is it affected by the current that you're trying to push through it, if we go down and look at the graphs, we can also see that the RDS on is also affected by our gate voltage. Right here, we have the RDS on and gate voltage, and they've normalized it with a 5 amp drain current. But you can see here what happens with the RDS on as our gate voltage increases. And they're showing 2 graphs here to show you the difference between it even when there's a temperature change. So everything goes into play when you're trying to calculate the wattage of this part to spec it out correctly. What's your gate voltage? What's the current you're going to be passing through it? What's the temperature that you're going to be operating in? You got to take all these into consideration in order to determine what is the best MosFET for your application. The final thing that I want to show you that I won't go over in this video, but in the last section of the graphs, if you wanted to use this graph in a switching circumstance, right, it takes on a little bit different characteristic because no longer are you running continuous current. All the prior things that we were taking into account about the 10 amps, the 5 amps, the RDS on, and that is based on a constant current, right, the continuous current mode. But if you are doing a switching current mode and you are trying to pulse something, then what you need to go is look at these graphs because you can push a MosFET farther than those specs if you are pulsing current. If you are pulsing current, it depends on how long your pulse lasts, determines how much current you can actually safely push before you actually get a degree C rise that becomes troublesome. So when you're looking at these graphs, you take into consideration the maximum safe operating graph, the single pulse maximum power dissipation graph, and the transient thermal response graph. Using this, you can calculate how much power the MosFET can handle and how much current you can really push based on single short pulses rather than a continuous current discharge. So that'll conclude the spec sheet explanation of how to spec out a MosFET, how to choose the right MosFET based on your application. So the next episode will actually go into a design sequence and we will try to use a MosFET in different scenarios run some simulations and calculate exactly how much power is being dissipated over a MosFET and see how these work in design applications themselves. So we can come to understand what it is that we really need to do and what limits the MosFET may have. Because even though you read these nice features up here that say, oh, 10 amps, 30 volts, short RDS on, after we read the graphs, after we understand our application a little bit, we come to understand that these numbers are nice. They're good reference points to tell you if you're on the right track. But you really got to dig into the details on the spec sheet to understand exactly what this component is going to do for your application. So thanks for watching and staying with me till the end. And like I said at the beginning, like, subscribe, share. If you like the video, comment down below. And I will see you in the next episode where we go into some designs using the MosFETs.